Hello everyone, thank you very much for being here this morning. It's not easy after a good evening out. So today I'm going to talk to you and give you a bit of an overview of the work I've completed so far. And of course I do have another year at Karlstad University, so we have more things planned. But my project, the ESR project, is novel guidance devices to support the downstream migrating fish. And I've also tried to develop the current barriers that we know already things about, but maybe not been tried with some species. And most of my supervisors are here today. I want to thank them for traveling all the way over. But let's get started. So today I'm going to go through a few things. So a brief introduction that I'm not going to spend too much on because we already heard a lot about the problems fish are facing. And I'm going to go through the experimental facility that we did use for most of our projects. And then just talk you over through an experiment we did with eel, with net and bubble curtain, that a lot of you have heard a lot about, but maybe not the people online. And then go through some of the other experiments that we also carried out: dancing rod barrier, injector flow, and some of the stress studies. But I'm not going to go into too much detail there. So, as we heard yesterday and this morning already, fish are declining. I'm not going to go more into that currently, but of course hydropower, as we also heard, is probably the largest renewable energy source globally. And it's actually set to expand further 8% in Europe by 2030. So 28% of that, as we also understood yesterday, is actually going to take place in protected areas, and in the EU that's 33%. And this is a scary thing to think about. So basically what we need to do is we need to make sure, and the European Water Framework Directive is making us think about it more, that we need to ensure connectivity in facilities. And of course, longitudinal connectivity, as we heard from Mule, should be a two-way street. So we should ensure downstream migration in addition to the upstream solutions. However, during downstream, one of the issues that we're facing, even when we have a fish passage installed, is that fish do follow bulk flow. So this is their instincts. They want to get with the main flow in the river to the sea. So what happens is, usually the main flow ends up in the turbines, so then the fish would instinctively just want to go with the main flow. And the question is, how do we get them then in the fish pass, either a nature fish way or a bypass, or how do we get them where we want them to be? And of course we could try and guide them there, and as we heard from Mule, one of the ways to do that is through fish screens, physical barriers. They could be inclined or they could be angled, from what we saw in his presentation. But there is an issue with them. So the issue here is that they're quite hard to upscale when you're talking about larger dam facilities and rivers, because they could be expensive for the company to build and maintain, and also they could be quite hard to, there could be a lot of safety issues with them. So another way that we could guide fish is through behavior. So we could use light, sound stimulus, bubble curtain that I'm going to talk about more, electricity and so on, to try and get the fish to the bypass, either through attraction or if they're trying to avoid a stimulus. And then we have hybrid barriers, which are kind of combination of methods, either behavioral stimulus or physical barrier with behavior. But I'm going to try and concentrate more on the behaviors ways to do guiding, and also mention briefly about a physical barrier we tried. So of course it's really hard to go ahead and try those things directly in a river because it's expensive to do, and of course you might need an environmental permit. Now we waited a long time for one of ours. So one way to do this is, if this thing could work, no, but it's to do this in a large flume. And the experimental facility at Vattenfall presented a great opportunity for us to do that. So it has a couple of arenas, they're all interconnected. Yeah, and I'm just gonna play a video here because I think it says a lot about the scale of it. A lot of you have already seen this, but again, the people online might not have. And I'm just saying a little aquarium because it's obviously very, very large. but it uses river water, so sometimes it could be like a challenge for, say, an automated recognition of camera of video footage. So a lot of it is, once you record it, you need to analyze by yourself, but hopefully that improves. So the first trial we carried out there was with eels, and we tested a bubble curtain. Again, I don't think this works very well, but no. But the top picture is basically a bubble curtain that we tried, like a behavioral barrier, and we kind of tried to compare the performance with a net barrier, so a physical barrier, but that hasn't been used so much previously, and see how it works with eel. And we had 9 cameras recording on both sides of the flume. And then we tested 4 different velocities. So we essentially had something like 12 treatments. And this is basically the results we got from it. So the net curtain, the net barrier did have significantly higher performance compared to control. And if you could see here, bubble, which was in red, basically underperformed compared to control. So more fish found the bypass over time with the net compared to bubble. And I'm just going to mention, so the eels were released here in the start box. There was a PTAG reader that took the recording when they left, and then we had a PTAG reader taking the recording at the end of the bypass. So this is how we knew if they passed and what was the passage time. And then for the rest of the place, we did have the cameras recording. So then we had to rely both on PTAG data and behavioral data. So this is what the PTAG data did show. And this is how many of them found the bypass over time, so the guidance rate. And what we saw with the behavioral data is kind of supported those results. So now I'm moving on to the dancing rods, which is a novel barrier developed at Vattenfall idea by Patrick Andreasen. And you already saw the video yesterday, maybe in the theater, but for the people that were online, I'm just going to play this. Yeah, so this is briefly how it works, and then this is what you see underwater. So this is just a snapshot of it near the bypass entrance. So the fish could go physically through, but instead it continues onto the bypass, and this thing here with the net is the entrance of the bypass. So for this one, it was just like a novel concept that we wanted to test it, and it was basically 45 pool noodles placed on a beam. And they were placed 15 centimeters apart, so there was plenty of space down here that the fish could pass if they want, and they were angled at 30 degrees to the flow. Okay, so this is the setup, more or less. Again, similar to the previous experiment, the fish was placed in a start box, PTAG reader took the recording, and then another recording was taken at the end of the bypass with cameras recording throughout. We had a surrounding velocity of 0.35 meters per second, and this time we used 16 cameras, but we then narrowed it down to 6 cameras that were relevant and analyzed, and we tested with 1-year-old smolts and with 2-year-old smolts. So the data, with PTAG data from the 1-year-old, shows quite high guidance efficiency for the rod, so that's percentage of the fish that reached the bypass. So for the rods was almost 70%, and the amount of fish that did find the bypass by chance, so when we had no barrier at all, was 24%. And the mean passage time was again significantly different. There was a lot quicker, 29 minutes versus 53 for rods compared to control. So hopefully we could upgrade that material and then test it further. And I just want to mention the 2-year-old data kind of follow the same trend, but with the 2-year-old, the fish did not even find the control very often, although that was only 8 trials. So then we moved on to testing an injector flow in the flume, and the purpose of this is to create an additional flow that could try and guide the fish towards the bypass or where they need to go. So the idea is, because they follow this main flow, creating an additional one could hopefully help them find a way or affect their behavior in some way. And we tested this with kelts. So this was quite interesting because we caught, not we, but the angling club in Dalalven caught 60 kills for us on the first day of May last year, and they were brown trout. So we had some salmon, but there were very few, so we went ahead and tested with brown trout wild kills. So the idea here is basically the fish was allowed in the flume, and the same group of fish, 5 fish, went through different treatments. So they were first, say, that was randomized, of course, exposed to a control where the jets weren't on at all. And then maybe we had the right jet on afterwards for an hour, and then we recorded how they swam. And then we turned that one off, and we had the jet on the other side that you could see kind of there are 2 inlets. We had the alternative jet on from the other side, and the fish went round and round, and we recorded how they swam. And we also continued the experiment with hatchery smolt, but I'm going to talk to you further about this in a moment. So what we did was we basically placed some of the cameras from a bird viewpoint, and here you could see some kilts moving where I've circled it. We had 29 cameras filming, some of them from a bird viewpoint, some of it from the side of the flumes, plus an iris sonar. But unfortunately, the iris sonar didn't work so well when we had the jets on, because from the bubbles you couldn't see so well the fish, especially with the smolts later on. So for now, we ended up just analyzing the video data. And what basically I got, we just wanted to mention that we had to do different settings of the high setting and the low setting of the jets, but so far I've just analyzed the jet side. And what we had briefly, I'm just going to talk to you about the results. When the fish were given when we looked at the left side swimming direction, analyzed that result. When the fish were given the left jet, it was a little bit less they used it compared to when they used control, and when they used, compared to when they use it during control treatment when there's no jet, and when we had the right jet on. So, yeah, basically they avoided it, a slight avoidance by the looks of it. And similar thing happened when we had when I analyzed the data of how much they swam on the right side. So when control treatment was on and the left jet was on, they were swimming, a little bit more on that side, on the right. But then when the right jet was on, the same as that direction, then they swam less on that side. So there appears to be some kind of an avoidance effect to the jets. And I need to go further into the data and see if that was significant and so on, but this is something I'm working on currently. So then we continued the experiment after we finished with the kilts. We also run through that some hatchery fish, Atlantic salmon this time. And what we did this time, instead of doing like this, like a repeated measure kind of setup that I told you we did with the kilts, we sort of did the smolts were placed in a start box here, this like a white thing you see on one of the sides, and then they just did a semi-loop. So again, we have the white block, this is where it was blocked for them, so they just kind of did one loop, a semi-loop, and then we had 1 hour for that. And again, cameras were recording and a DRS, but this time we only used the lower jet setting, since the swimming capabilities of smolts might be lower than kilts. And what I had here, so I turned this into percentage, how often, like in a trial, they swam on each side. And again, we had the different treatments, the right jet, left jet, and control. And when they were given the right jet, so they swam, they seem to have like a preference for the left side, what we see in the right jet and during control. But when they were given the left jet, they did swim a little bit less on the left. So what's interesting here is, although I don't think we see a big effect at all from the jets, is that we see that the smolts are using a preference of swimming, and then that links well to Sophia's data that she showed yesterday. She took stress measurements on those smolts. So there's definitely maybe a thing causing them to be more stressed because they cannot select the swimming direction that they prefer. So yeah, I just wanted to link it to that. And what we're going to do next is we're going to actually try the injector flow in a river, because in the flume, of course, you could have some, more like hydraulic conditions that are not optimal. So what we're going to try and do next autumn is actually test it at one of the sites at Klarälven at Edsforsin. We're going to create like an additional flow through this pump, xylem pump, and then with acoustic telemetry, try and figure out if the fish were affected by the presence of the pump and the jet current. And yeah, so looking forward to doing that work. What I also did during this project is I got kind of interested in what the fish are experiencing during downstream migration and those different barrier solutions and passage conditions that they might go through and different stress factors they might be exposed to. So one of the things I thought about trying to test is maybe the heart rate as an indicator of stress. And we set up kind of on the site, we did have some fish tagged with, from the 2-year-old dancing rods experiment, and then continued working with them and kind of trying to put them in a novel situation to see how does the heart rate differ. And what we thought about is placing a fish by itself in a novel situation, and then placing it with another fish from the fish they knew from the fish tank, or maybe from a different fish tank and age to see how they react. So the fish was placed by itself in a novel situation, or else with 5 fish it knows, or with 5 fish it doesn't know. And what I had here as a result was quite interesting. So the alone fish, this is the percentage of heart rate increase from the resting heart rate. So the alone fish was significantly more, had a significantly higher heart rate compared to when it was placed with fish they knew, or even with fish they didn't know. So that didn't seem to make a massive difference. So from then onwards, we got the idea with Sophia to carry out further experiments, and this was the setup we had, camera at the top, and then 6 fish by themselves and alone. But I'm just not going to talk to you further about this because she went very in detail yesterday. But what we're going to do further is analyze the videos for this hierarchical organization that she talked about yesterday, and see if they exhibit behavior, what kind of aggressive behavior they exhibited to each other, and how that linked to heart rate. So I think that could be just interesting, like a little side experiment from my overall thesis and topic. So yeah, I'm gonna go through a little summary. So the net for eel did not seem to work quite well compared to control and bubble. So we believe it has some potential for fish guidance. While the bubble curtain for eel, the guidance rate was the same as control, so low potential for guiding eel at this point. The dancing rods for salmonids, I've misspelled something here, but anyway, so we have a higher guidance rate compared to control, and we believe that if we upgrade the material, there is a high potential for fish guidance in rivers. For the jets, so there seems to be some kind of an influence on swimming direction, some evidence of avoidance. So following trials will hopefully give us a clearer view of what's going on there. And jet strength might play a role, so how, of course, strong is the jet. During the stress studies, we saw that heart rate response was quite different in the different salmonid species, between trout and Atlantic salmon. And the heart rate is not always suitable for measuring acute stress response, because when the fish is in a novel situation, like the heart rate is already quite elevated, so maybe not best to then try and pinpoint certain events. So there's maybe other stress factors that are better indicators there that Sophia talked about yesterday. And just what is the final take-home message? So what do we have potential here to upscale? The net, I think it has a good potential, the dancing rods and the jet current. So that could serve as some potential solutions for this upscaling problem that we have with physical barriers. So with this, I want to thank everyone for listening, and special thank you to my supervisors, collaborators, both from different Vattenfall and SLU and different organizations, and thank you to my ESR collaborators and all of the ESRs and the RIBES consortium for all the great advice so far. Thank you very much.